So, last class we started relation between current, drift velocity, current density, field, relaxation time and drift velocity, and field and current density. So, till now we have discussed these relation. So, if current density if we apply field in a conductor by connecting it through a cell, then due to this application field is created inside the conductor. As field is created inside the conductor, electrons start drifting opposite to the field, and we got the relation between current and drift velocity as I is equal to NEA Vd, right. And if I divide this I by area, I will get current density. So, current density was J is equal to E N Vd. Minus sign indicate that both will be in opposite direction. So, as current start flowing in this direction, current density will be in same direction. Direction of current density is same as the direction of current, but you can see that drift velocity is opposite to the direction of current density. So, minus sign is because both I and Vd they will be in opposite direction, right. And then we found the relation between drift velocity and relaxation time. So, drift velocity related to relaxation time this way, right. Here relaxation time is what we discussed in the last class, is the average time between two successive collision, right. So, drift velocity depends on relaxation time, field applied, E and M. For a given material, we have seen that the relaxation time is almost independent of the field applied. So, for a given material, this E, M, tau, these value will be constant. Higher the field applied, higher would be the drift velocity, that we can say. And then using this relation and this relation, we got J is equal to sigma E, where sigma was thermal conductivity, sigma was conductivity, right, and the value of sigma was N E square tau by M, right. So, for a given material, number of free electron per unit volume will be known, relaxation time given, you can substitute here and you can find out the conductivity of material. Conductivity of material is reciprocal of resistivity of the material, like, so resistivity of material is 1 upon conductivity of material. So, this is what we did in the last class. Let us see what we have today. So, using J is equal to sigma E, I can derive Ohm's law. So, when I connect potential difference delta V across two ends of the wire of length L, area of cross section A, then and due to this potential difference a current flowing through the conductor is I. So, I want to establish the relation between this delta V and I. So, we know that J is equal to sigma E, right. E, this E is the field inside. So, if I call it E, the value of field inside, we know that dV is equal to minus E dot dr. So, from here I can write delta V is equal to E into L. So, the value of E I can substitute from here, and this J, current density, is current per unit area, that I can substitute over here. So, and rho we have just seen, sigma is equal to 1 upon rho. So, I can substitute sigma is equal to 1 upon rho. So, all these values I will substitute. So, E can be written delta V by L and J can be written I by A, that will be equal to sigma, right. So, if I rearrange this one, then I will get R is equal to delta V by I, where this R is. If you rearrange this one, then what you are going to get, R is equal to rho L upon A. So, L will come here, rho if you multiply. So, this we are getting so resistance offered by conductor is given by formula rho L upon A, right. So, as I already use all this, I can erase. So, resistance offered by this rod to the flow of current is given by R is equal to rho L upon A, where L is defined along the direction of current. As you can see that current will be flowing this way, this current will be flowing this way, this is the direction of current, and we are defining current along the direction of length. So, this is along the direction of current, and the A what we are writing here is perpendicular to the flow of current. Current is flowing this way and the area of cross section is A. So, this is perpendicular to the flow of current. Right. So, here you have to carefully substitute all the value to find out the resistance offered by the rod to the flow of current. So, R is nothing but the measure of electrical resistance of an object is the measure of opposition to the flow of current. How much material is offering opposition to the flow of current, measure of that is called resistance, right. And its SI unit is ohm, that is also written this way, right. So, this is a symbol of resistance or symbol of ohm. So, I hope this part is clear. Now, look at this one. If this is constant for a given material, this will be constant. I can say from here delta V is proportional to current. So, we apply potential difference across the material and the current flowing through it will be proportional to the potential. Such type of materials are called ohmic material and this is called Ohm's law. So, it is not necessary that all the material obey Ohm's law. It might be like voltage difference might be proportional to I square I to the power minus 2 by 3, or it may be any other function. If it is directly proportional, then the material is said to be ohmic material, right, and the proportionality constant is called resistance of the material. Now, if you remember how we define capacitor or capacitance, we gave Q charge and we calculated the potential difference. This is the way we define capacitance. So, this is the basic definition of capacitance. By giving charge Q, what potential difference you are getting across the two terminals or across two plates, that ratio is called capacitance. Similarly, to find out resistance of any substance, what we can do, we will calculate the potential difference and we will divide by current, we will get resistance offered by that conductor to the flow of current. So, this is the most basic definition of resistance, like we had the definition of capacitance. Okay. So, I hope this whole thing is clear. Let us move to next slide. Now, we are writing R is equal to rho L upon A. A cross sectional area, L length, rho resistivity. So, if I stress the wire, what happens to the resistance? If we stress the wire, what happens to the resistance? So, R is equal to rho L upon A. When you stress the wire, the volume will remain constant and we can write this whole term in terms of volume, so that we can decide. So, multiply and divide by L, this will be volume, and in numerator you will get L square. Okay. Now, if there is a small change in length, how that will affect the resistance of the wire? If I take log over here, right. So, ln R will be equal to ln rho by V, volume is constant, I will take this term with this one, and plus ln L square. If I differentiate this one, then I will get delta R by R is equal to, as this is constant, this value will be 0, 2 times delta L by L, delta L by L. So, you can see that twice of fractional change in length is equal to fractional change in resistance, or I can say that if here fractional change in length is 1%, then resistance will get changed by 2% multiplied to 2. So, it will become 2 times. So, I hope this part is clear. So, delta R by R is equal to 2 times delta L by L. Do remember that what we are doing here, that can be done only when change is small. If change is large, then we cannot take log and differentiate, right, to find out fractional change in resistance. What we need to do, that we will see later. But for time being, for small changes we can just take log and differentiate. Okay. So, first case what we have done, we took wire and we stretch it by very small amount, and we are seeing that how much is the fractional change in the resistance. Now, what if I change or reduce area by stretching it, area will also get reduced, then what would be the fractional change in resistance? So, same way I can write. Now, I want expression in terms of area. So, what I will do, I will multiply and divide by area now. So, if I multiply and divide by area, this will be A square. Okay. And if I take log and differentiate, so ln R is equal to ln rho divided by A square plus ln V, right, A rho and V both are constant, I will write here, this is 1 upon A square, right. So, this 2 will come in the front, and we can see delta R by R will be equal to, this can be written minus 2 in front. So, get this term up, and this will be minus 2 delta A by. So, minus sign here indicates when area reduces, resistance increases. That means if I take wire and stretch it and area is decreasing, the resistance of this one or wire will be increasing, and this is the relation. So, if I say area is increased by 2%, then resistance, area is decreased by 2%, then resistance will increase by 4%. Okay. Same way we can predict what happens to the resistance. So, delta R by R is minus 2 times delta A by A. Now, what would be the relation between fractional change in resistance and the radius of cross section of the wire? If I am taking cylindrical wire, then wire is stressed so that there is decrement in the radius, right. So, same expression rho L by A, there I will convert into A square and will make it volume, and here I can write, if it is a cylindrical conductor, then I can write pi r square. So, pi r square whole square will give you r to the power 4. So, if I take log and differentiate, this minus 4 will come in front, same way what we have discussed just now. So, fractional change in the radius will be minus 4 delta r by r. So, if radius is decreased by 1%, radius is decreased by 1%, then resistance will increase by 4%. Okay. If we are stretching the wire, if you cut the wire, then situation will be different. R is equal to rho L upon A. If I just cut the wire in 2 pieces, so that this total length was L, this total length was L. If I cut into 2 pieces, then this length will become half and resistance will become half, right. So, resistance reduces when length reduces. When you cut, you are cutting the wire. Here we are not cutting the wire, we are stretching the wire. So, stretching the wire, we know that volume is constant, we try to get the whole expression in terms of volume, and we can relate resistance with the length, we can relate resistance to the area, and we can relate resistance to the radius, right. So, I hope the formula is clear. R is equal to rho L upon A. First point was L is the length along the current, A is the area perpendicular to the current, and if we are stretching the wire, we can relate any of the physical parameter with the resistance by keeping volume constant, right. So, this whole thing is clear. Let us move to next one. So, based on what we have discussed, let us see one example. So, we have got one wire and we are stretching it and we are increasing length by 10%. I already told you for 1%, 2% you can use the method we have discussed, but if increment is large, for example 9%, 10%, 11% or more than that, so for that we cannot take log and differentiate to find out fractional change. For such type of condition, what we have to do, now see, R is equal to rho L upon A, okay. Here density of wire is given. So, in terms of density, if we can write, so if I multiply to length here and here, this will become volume. Volume can be written mass by density. So, mass by density I can place here, and if I just simplify, L square I will take out, this is a constant. So, this whole thing is a constant into L square, right. So, R1 is some constant into L square, that means resistance is proportional to length. Now, what you have done, you have increased the length by 10%. So, you are increasing the length by 10%, new length will be. So, increase length by 10%, another 10%, so total length will become 1.1 L, and the new resistance will be 1.1 into L whole square K times. So, new resistance will become this, old resistance was this, divide K will get cancelled out and we are getting this one. Now, we want to find out percentage change in the resistance. For percentage change in the resistance, R final minus R initial divided by R initial into 100, right. This is percentage change in resistance. So this will become R2 minus R1 divided by R1 into 100. That means R2 divided by R1 minus 1 into 100. R2 minus R1 I can substitute here. So 1.21 minus 1 will give you 0.21, multiplied to 100 you will get 21%. According to the previous slide, delta R by R is equal to 2 times delta L by L. So if we apply this formula, then delta L by L 10% into 2, this is coming 20%, right. But actually what we are getting? We are getting 21%. So as I already told you, this is applicable only when the change is very small, 1%, 2%, 3%, for that you can use this. But if change is large, then we have to follow this procedure. So many times such type of question came in JEE, and students generally commit mistake while calculating fractional change by just taking log and differentiating. Before taking log and differentiating, you have to make sure that the change is small. Okay, if change is large, then this is the procedure. So this is wrong. So I hope this concept is also clear. Now let's move to next one. So one cylinder is given, it's hollow cylinder, the radius of inner surface is A and outer surface is B, and let the length of the cylinder L. Okay, resistivity of the material we have is rho. Question is, find the resistance of the cylinder if source is connected across. So first case, we are connecting source this way. Okay, so we are connecting source across two ends, and when you connect source across two ends, current start flowing through conductor along the axis, right. Two ends are maintained at different potential, so current will flow from higher potential to lower potential. What would be the resistance? So formula is R is equal to rho L upon A, right, where L is the length along the flow of current and A is area of cross section perpendicular to the flow. So for this situation, the current is flowing this way, right, along the axis, and it is facing this area while entering into conductor, and throughout the conductor the area current faces is this only, and the length current is flowing through is L. So here I can write L, this is rho into L divided by area current faces. We can calculate this area, that is pi B square minus pi A square. So this is the resistance of first part, okay, part A, simple. Now second part, the inner and outer surfaces are connected across the source. So if we are connecting instead of ends, if we are connecting instead of connecting this way, if I connect source this way, so inner surface connected to positive terminal of battery, right. So now as there is a potential difference between inner and outer surface, current will flow from inner surface to outer surface because inner one is maintained at higher potential. So instead of current following this way or moving along the axis, now current will be perpendicular to the axis, okay, from inner surface to outer surface. Let us see what is happening. So I will draw this cross section first. So this cross section I am drawing, this is representing cylinder coming towards you, length of cylinder is L. Okay. So this is the cross section and the direction of flow of current. Current flows from inner surface to outer surface. So current will be flowing like this. Now if this is the way current is flowing, and if I consider cylindrical shell of radius r of thickness dr, this way. So just look at this part. I have considered cylindrical shell of radius small r of this thickness dr. If I ask what is the resistance of this part, okay. So previous case you maintain potential difference this way, current was flowing like this. Now you are maintaining potential difference this way, current will move from inner surface towards outer surface this way, right. So if this is the conductor, current will be flowing this way in every direction perpendicular to the axis of the cylinder, right. So if I ask what is the resistance of this part dr, dr is equal to rho L upon A, rho L, length through which current is flowing. So here as current is flowing in this direction, this thickness is dr, so length through which current is flowing is dr divided by the area current faces. If you look at this one, then there is a cylinder coming towards you, the surface area when current reaches up to r, this surface area is 2 pi r into L. So area current faces is 2 pi r into L. I hope this part is clear. Whatever we are writing here, that is along the flow of current, and area is perpendicular to the flow of current. So if I integrate this function, I will get the value of resistance. So let us integrate. Limit from this inner surface to outer surface total resistance. I want to find out total resistance. I am integrating this one. I am adding resistance of all such coaxial cylindrical shell, right. So I am adding all the resistance from A to B. So, if I integrate, I can see rho 2 pi L, these all are constant, integration of 1 upon r, ln r upper limit minus lower limit, directly I am writing ln b by a. So, this is what we are getting resistance as. So, inner and outer surfaces, if source is connected, the resistance is rho divided by 2 pi L ln b by a. Earlier we were getting something else. So, first case rho L upon pi b square minus a square, second case rho upon 2 pi L ln b by a. That means for a given material it also matters that how current flows, and accordingly you are going to get resistance. The same cylinder I am connecting, across two ends I am getting this resistance. When I connect battery across two surfaces, then I am getting this resistance, right. So, to decide what would be the resistance, you need to know the way current is flowing, and accordingly we will substitute the value of length and area, and we are going to get different result. Now, in both the cases one thing is common, that resistance depends on the material, resistivity and the dimension, resistivity and dimension. Okay. So, while calculating resistance, this is what you have to keep in mind, how current is flowing. Accordingly we will substitute value and we will integrate if it is required. Now, most of the question, the complication, if you look at R is equal to rho L upon A, it might be possible that area is given as a function of distance. Different area will be having different cross section will having different area. As you can see here, when current is just getting into the inner surface, the area it faces. So, visualize yourself inside the cylinder and you want to cross the cylinder perpendicular to the axis, you want to go like this, just down. So, if you are inside the cylinder and you are crossing the cylinder perpendicular to the axis, then the area you are going to face when you are at inner surface, that will be 2 pi a into L, and when you are about to come out from the outermost surface, then area there will be 2 pi b into L, right. So, everywhere current faces different area. So, one complication can be area as a function of distance, and another complication will be resistivity as a function of this. Resistivity as a function of distance. So, maximum two complication can be there. One we have already seen, that area as a function of distance, and the second one resistivity as a function of distance. Let us see. So, let us take one more example so that whole concept is clear. You can read the question. So, rod of length L, area of cross section A lies along x axis between x is equal to 0 to x is equal to L. So, we kept the rod, and it is given that material follows Ohm's law, means whatever potential we are applying and the current we are getting, they are directly proportional. Okay. Here the resistivity varies according to this expression. So, the previous case I took resistivity constant, in this case resistivity is varying. Okay. Question is, find the total resistance of the rod. Here we are applying potential difference across the ends. So, this one is connected to positive terminal of battery and this one is connected to negative terminal of battery. Here we are assuming 0 potential and here we are assuming V0 potential, right. So, obviously current will be flowing this way, this is the way current is flowing. I want to find out total resistance offered by rod. So, as resistivity everywhere is varying and area everywhere you can see is constant, okay. So, I will first calculate the resistance of a small element. So, here I will take small element and I will try to get the resistance of this small element. Let the thickness of element is dx. So, for this element dr is equal to resistivity dx along the direction of current in numerator divided by area current faces. Everywhere area is same in this situation, rod cross sectional area is same. So, A is constant in this situation, A, okay. To get total resistance I need to add all drs. So, to add all dr we need to integrate limit from 0 to L. So, here I will write 0 to L. Rho is rho naught e to the power minus x by L, rho naught e to the power minus x by L dx divided by, okay. This we can simplify. So, total resistance rho naught I can take out, E I can take out, these are constant, and e to the power x integration whatever coming in front of x, that is minus 1 by L, that will come in denominator. So, I will write minus 1 by L, okay, and integration of e to the power x is e to the power x only. Then limit 0 to L. So, this is what we have. R is coming minus, if you send in then lower limit minus upper limit we can write. So, rho naught L by A in bracket 1 minus e to the power 1 e to the power minus 1 e to the power minus 1, okay. So, this is what we have. So, we got the resistance of whole rod, first part over. Now, look at the second part. Second part, find the electric potential in the rod as a function of x. If here potential is V0, what would be the potential here I want to find out? What is the potential here? So, let us call it Vx. I want to find out Vx, okay. So, electric potential Vx we need to calculate. When you connect it to source, through every cross section current will be same, whatever enters here that must come out, right. So, through every cross section current will be same. If current is same and it is following Ohm's law, then I can write potential difference, see potential difference V0 minus Vx is equal to I into resistance of this part. So, I need resistance of this part only, current into resistance will give you potential difference. So, I require resistance up to x only. This is the total resistance, resistance up to L. Up to x means I need to just change the limit. So, instead of this being L, now I require up to x. So, there itself I will change the limit. If this is x, here x by L will come. Okay. So, resistance up to, from here after changing limit I can write current into resistance up to x, rho naught L A 1 minus e to the power minus x by L. This is V naught minus V x. I need to just substitute the value of current to calculate the value of Vx. So, current is what? Potential difference across two ends is V naught. So, current is nothing but potential difference divided by resistance, potential difference divided by resistance. This value of current I can substitute over here, and after simplification I can calculate the value of Vx. Simplification you can do. I hope the procedure is completely clear. There might be only two types of variation. Either area will be changing with the distance or resistivity will be changing with distance. It might be possible that in example both variations are there. Area will be changing with distance as well as resistivity is also changing with distance. So, in the expression you substitute both the variation and integrate, you will get the answer, right. So, now I hope all such type of question you can solve. Let us move to next slide. So, you can verify this one. Okay. So, V naught e to the power minus x by L minus e to the power minus 1 minus e to the power minus 1 you are going to get. So, let us see one more concept. So, we have two materials, like earlier I was discussing only one material connected across the source and current was flowing through the same material. If I say we have got composite rod where two rods are joined, and what happens at the junction? Okay, so when two rods are joined, what happens at the junction? So, this is one material of conductivity sigma 1, conductivity sigma 2. Question is, show that, you can read it, show that the total amount of charge that the junction of the two material in the figure is E naught I 1 upon sigma 2 minus 1 upon sigma 1. So, the charge that gets accumulated at the junction is given by this expression, where I is the current flowing through the junction and sigma 1 sigma 2 are the conductivity of two materials, right. So, we want to know that when two different materials are joined, how much charge that gets accumulated at junction, okay, that is the question. So, to calculate this charge, we can use Gauss law, charge inside, we can use Gauss law. So, if I take Gaussian surface this way, this is cylindrical rods, both are having same cross sectional area, and I am taking Gaussian surface this way. As you can see that here, if I assume field E1, flux is entering into this Gaussian surface at this face, and here flux is leaving the face. If current density is same, because current will be same, whatever goes in that comes out, divide by area. So, current density here and current density in the second material both will be same. If current density is same, we know J is equal to sigma E. If current density is same, conductivity is different, then field will be different. Here this is E1 and E2 and you are getting inversely proportional. So, if sigma 1 is greater than sigma 2, that means E1 is less than E2, E2 will be more. So, flux coming out will be more and flux entering into will be less. Okay. So, what is the net flux? Net flux field into area. So, E1 into A, this is what is getting in, and what is coming out? E2 into area. According to Gauss law, E dot ds close is q in upon epsilon naught. So, net flux I have already calculated, I have written here, then q in upon epsilon naught. This is our first equation. Okay. And second equation, the J will be same because current is same. So, I can write E1 sigma 1 must be equal to E2 sigma 2 must be equal to current by area. This is our second equation. So, I can substitute value of E1 and E2 over here and by that I can find out charge in. So, let us see. So, now we are solving these two equations. So, E1 or E2, E2 is equal to I by A sigma 2, I by A sigma 2, okay, this over into A. Then in this one, E1 is equal to, similarly I can write I by A sigma 1 A is equal to q n upon epsilon naught. A gets cancelled out, A gets cancelled out and I can take out epsilon naught. If I multiply I epsilon naught in bracket 1 upon sigma 2 minus 1 upon sigma 1 is equal to q n. So, we have proved that charge at the junction will be given by this expression. So, two different material when joined, junction will accumulate charge in such a way so that it will create the field difference on both sides. One side we are getting field E1, another side we are getting field E2, right, because they are different material. So, I hope this concept is also clear. Let us move to next one. So, temperature variation of resistivity. Okay. So, we know that conductivity and relaxation time, conductivity and relaxation time relation we know, and if I increase temperature then relaxation time decreases. By increasing temperature relaxation time decreases. In the last class we have seen that. So, as you increase temperature relaxation time decreases. As relaxation time decreases, as this quantity decreases, conductivity decreases. As this quantity decreases, conductivity decreases. As conductivity decreases, resistivity increases because resistivity is 1 by sigma, right. So, when you are decreasing conductivity, resistivity will increase. So, I can say when temperature increases, resistivity also increases. When we plot the curve between resistivity and temperature, when we plot the curve between these two, then we get curve almost straight line. At the higher temperature, you can see that these points, these dots start deviating from a straight line, right. So, for a small temperature range, I can assume this relation to be almost linear, right. So, now I will erase all this. So, what we have concluded that for a small temperature range, the resistivity is proportional to temperature, I can say, okay. And why that is happening, that we got from the expression what we have derived in the last class. So, when we heat up the material, electron will have more kinetic energy. If electrons are having more and more kinetic energy, then they will frequently collide with the atoms, and as the collisions are more frequent with more energy, they are taking lesser time. So, relaxation time is on an average time between two successive collision. As time become lesser, the conductivity will also get reduced. Conductivity getting reduced, resistivity getting increased. So, material at higher temperature will offer more resistance to the flow of current as compared to the material at cooler temperature or lesser temperature, right. So, here we define a parameter called alpha, right. Alpha is coefficient of alpha, this temperature coefficient of resistivity, this is called temperature coefficient of resistivity. So, as you can see, this is defined for a temperature range. If curve is something like this, the value of alpha will be different at different points. As the curve is a straight line for a small temperature range, so value of alpha is almost constant for that small temperature range. This I am drawing temperature as a function of, or this side I am plotting temperature, and this axis is for resistivity. So, what I am saying that if we take a small temperature range, this relation is almost linear. If this relation is linear, this quantity will be constant, okay. If this quantity is constant, then I can also write here alpha dt is equal to d rho by rho, okay. And if I integrate alpha constant, alpha I have taken out, so this can be written ln rho is equal to alpha t limit. So, at t is equal to some t naught, if I assume resistivity is rho naught, and at some t resistivity is rho, this I am getting ln rho by rho naught alpha t minus t naught. This can be written rho is equal to rho naught e to the power alpha t minus t naught. So, for this small temperature range, I can expand e to the power alpha, and I can neglect higher powers because this is very small. So, if I neglect higher power, this can be approximated to rho is equal to rho naught 1 plus alpha delta t. If rho is equal to rho naught alpha plus delta t, then R can also be written as R is equal to R naught 1 plus alpha delta t. So, resistance of the wire varying with temperature, as temperature increases, resistance increases, and that relation is given by R is equal to R naught 1 plus alpha t. Similarly, we can write rho is equal to rho naught 1 plus alpha t. Now, in the derivation, we have assumed alpha to be constant. In any question, if alpha is given variable, you cannot take alpha out. So, if you cannot take alpha out, you need to integrate this expression with respect to t, then you are going to get totally different result. So, be careful whether alpha is given constant or alpha is given variable, accordingly we will proceed. If nothing is said, we will assume alpha to be constant, and according to alpha being constant, we will apply these two formula, R is equal to R naught 1 plus alpha delta t, or we can apply rho is equal to rho naught 1 plus alpha t. Okay. So, alpha is equal to 1 upon rho d rho by dt. Generally what happens, what we do, we define alpha average. So, when we are defining alpha average, alpha on an average, we will be writing 1 upon rho delta rho by delta t. This way we will be writing for a given temperature range. So, for example, like from 10 degree centigrade to say 50 degree centigrade, a particular value of alpha is given, that is on an average value, because the variation of alpha with temperature will be very small. As you can see, this is almost a straight line. So, you can treat, though it is varying with temperature, you can treat this as a constant. Okay. If you can assume this to be constant, you can apply R is equal to R naught 1 plus alpha delta t. So, I hope this whole concept is clear. Now, see, over the limited range, just now what we have discussed, over the limited range of temperature, the relationship between resistivity and temperature is nearly linear. Okay. So, I hope all these points are clear. So, you take a material, you heat it up, as you heat it up, its resistance increases, its resistivity increases. The reason behind that is reduction in relaxation time. So, relaxation time will affect conductivity, and that in turn will affect resistivity of the material. So, this whole thing is clear. Now, so finally you can write R is equal to R naught 1 plus alpha T. So, reference temperature will be given to you, and you can use the reference temperature. For example, if I say alpha is 10 to the power minus 3 for the given material, and at 20 degree centigrade the resistance of the wire is 2 ohm. So, 20 degree centigrade resistance of wire is 2 ohm. What would be its resistance at say 60 degree centigrade. So, I will write temperature here because I want resistance at 60 degree centigrade. I will write 60 over here, and after simplification I will get the answer to 1 plus this I can write 40 into 10 to the power minus 3. So, this will become 0.04 1 plus. So, this will become 1.04 into 2. Okay. So, resistance at 60 degree centigrade is given by this 2.08 ohm. So, this is the way I can use this formula. Temperature or resistance at the reference temperature will be given, and you can find out resistance at other temperatures, right. Now, so how the heating will affect the flow of current, let us see that. So, I have two conductors maintained at two different temperatures. Okay. Let us say temperature of this one is T2 and temperature of this one is T1, and I am considering T2 is greater than T1. So, same material, same dimension connected across same source. So, potential difference across here and potential difference here both will be same, and the only difference is one is having temperature larger as compared to another one. So, this is at T2 and this one is at temperature T1. Okay. So, higher temperature wire will offer more resistance, right. So, as you can see, when switch is closed, they move slowly, drift velocity will be less as compared to the one which is at lower temperature. There the resistance will be less and the movement will be more. So, here as T2 is greater than T1, the resistance of 2 will be greater than resistance of 1. We have just seen as temperature increases, resistance increases, right. So, higher the temperature, higher would be the resistance, and if they are connected across same source, the current flowing I is equal to V divided by R. Higher the resistance, lower would be the current. So, what I can write, higher the resistance, lower would be the current, I1 will be less than I2. So, this is the way all the quantities will be related if one is at higher temperature as compared to another one, right. And one more thing, because of the temperature you can see that these ions, they cannot move through the material, but because of the temperature they will be vibrating, right. But they are vibrating, they are fixed in the location, they are not moving from one part to another part, but these free electron, as they are free to move, they can move from one part to another part, they start drifting. Okay. So, more the temperature, if I take same material, copper of same dimension, right, one is at lower temperature, another at higher temperature one will be offering more resistance and current through that will be less. So, I hope this whole discussion is clear. So what we will do in next class, we will discuss numerical based on this concept, and then we will start series parallel combination, right. So next class we will be talking about series parallel combination, and we will see more numerical from this topic. So I hope you enjoyed today's class.